Nope.
Oh, just skip onto that. Yeah. That's fine. I've never seen so many pizzas go so fast. There's lots of beers left, so if you want a few drinks, help yourself. But we're moving on to the second talk now with from Aerospike. So, yeah. Okay. To talk into that as well.
So, hi everybody.
Hi.
Hello.
Hi.
Okay, so now that everybody's dined and wined, let's start the second talk. My name is Behrad Babaee. I'm a technology evangelist in Aerospike. Aerospike is a database company. So the title of this talk, I have to read it, it's so long I forget it myself. It's Design Patterns in the Streaming-Enabled Database Technologies, right? It's a mouthful, and I think the first thing I should do is to just explain what this title actually means. So design patterns are basically a bunch of canned solutions that you can apply to some recurring problems in software applications. So you've possibly seen some of these design patterns before and you use them if you are developers. But basically, software engineers, for a long time were solving similar problems. They thought that it's a good idea to put all of these problems, basically having common solutions for these problems, giving them a name, so when they are trying to solve those problems, they can just very easily open that can, apply the content of the can to the problem, and just get on with their lives and doing the most interesting part of the problem. So that's the design pattern part. So now I want to talk about the streaming-enabled database technologies. I have to be a little bit descriptive here. I'm not talking about the streaming databases. Streaming databases are a different kind of databases. I'm gonna explain what the streaming-enabled databases are in the next few slides. So let's first talk about the streaming. So this is a Kafka meetup. Hopefully all of you know what streaming is, what are the topics are. You usually show streaming in your UML charts with something like this. It's basically a pipe. You have a producer and you have a consumer. The producer creates things independently of the consumer, push it into the pipe, and then that pipe sometimes later somebody can consume that. Sounds very different to databases, but it is actually not that different. Even you can say that if you just invert that pipe a little bit, right, it becomes kind of like databases, right? It's not that different, right? If you think about it, it's almost the same. We just inverted that cylinder and we called it writer and reader instead of producers and consumers. And it's almost the same, but in reality, they are slightly different. So now I want to ask this question. Who can define a difference between streaming technologies and databases? Just give me a guess. Come again? No? Nobody? Transactions. Yeah, that's the difference. Data in motion, that's getting closer. That's good. That's good. But if I want to put it in a a simple term, I would say that streaming technologies are generally better for sequential access to the data. Databases are better for random access to the data. But it doesn't mean that either of these technologies cannot do the other one. So using a streaming technology like Kafka, you can have random access to your data. And using your database, you can have sequential access to your data as well. This is just like one of them, each of them is designed for something, but they are really so close. You can do one with the other one as well. If 95% of your problem is streaming and you just have a little bit of random access, you can possibly do it with just the streaming technology. And like if 95% of your problem is data storage and random access to the data, you can possibly do the streaming related part with the database as well, right? Very, very similar things. But there are many, many use cases that you are 95%, 5%. You need both of them. And it goes with the previous talk topic that it's not and or, it's usually and. You usually need both of them. And we discussed about this one as well in the previous talk, that we said that yeah, you can have producer and writers writing into the database and writing into the stream at the same time, and then you can have consumers and readers from the database. In the previous talk we talked about real-time analysis and batch, but I don't know, reader is not necessarily a batch. Reader can be just a lookup that possibly even used by the consumer, right? The consumer may need to enrich the data that is coming from there with something else in the database. So you want to basically access the database to do a lookup. So you need both of them. But I completely agree with the topic in the previous talk that this is not a good idea to write it to have one producer or one writer writing into both of these different technologies. Well, the main problem with this is that who's going to confirm the consistency between your streaming technology and the database technology, right? You might write to the database and the write to the streaming technology fails, right? Or the otherwise. How you are going to make sure that both of these technologies receive the piece of information that you want both of them to receive. So I would say this is a better kind of architecture for these kind of things. So basically, you write into basically one thing, and that one thing, write it into a, it can be either this, that it writes it into a topic, and your database automatically subscribe to that topic, and your database receive the things that you want it to write, and you get the real-time sequential reader out of this whole thing, and you also have random access reader from this, all of this technology. Or it can be the other way around. The database can be, the main receiver of the data, and the database publishes the data into a topic. And then again, the result is the same. You have a random access reader and a sequential reader at the same time. And if you have a technology that can do both of these, you can end up with something similar to this, that you have a topic at the top that is providing you with the real-time access to the events that are happening in the system. You have something in the middle that is providing you with random access, right? And the last one can provide you with something like an events-based system. I'm going to talk about that in a second, that's what I mean. But this, this sounds really good, right? And you've possibly seen many of these technologies before, but they usually don't work, right? Reason for that is that they are ridiculously slow, right? Now I'm gonna get a little bit more theoretical, and I'm gonna explain to you why these systems are usually very, very slow. So, when you have different technologies, and especially that all of these technologies are distributed technologies, their latency is exponentially increasing with the number of nines in the percentile that you are looking at is increasing. So let me first define latency and percentiles, because it's important for the rest of this stuff. So imagine you have a system and you want to measure the latency of the calls that you are making to this system, right? So imagine you make, 1 million requests to this system, and you log the amount of time that it took to for this system to answer the request that you send. So if you put all of these response time in a list and you sort it all from the fastest to the slowest, right? So you have a list. This is the slowest. This is the fastest. If you get the item that is right in the middle of this list, the 50th, the item that is in the 50th percent, that's the 50th percentile of the latency to that system. If you go to the 90th percentile, that's the time that is in the 90th percent of this list is going to be the 90th percentile. As you increase it, as you go to 99, 99.9, 99, 99.99, the latency increases exponentially. The reason for that is that it's a distributed system. Things go wrong in distributed systems. Your network's gonna have problem, your disk's gonna fail, your machines are gonna fail. So as you increase the probability of having these items, the things start to become exponentially slower. And as we said, in distributed systems, that's what you always have. So the thing is that when you creating a service, that services usually come with some kind of a non-functional requirement. That non-functional requirement is usually in the shape of a SLA. The SLA says that the service must have a latency at a specific percentile less than some milliseconds. For example, it must be faster than 100 milliseconds at P99, right? Okay. So when you are looking at this service that you want to create with that latency, that service is usually made of some sub-operations. Now, it has to make different things. Let's say it has to make several database calls. It has to go to Kafka. The Kafka may publish it to another database. I don't know, lots of different things. So you have n sub-operation in your service. If we define the latency of each of those sub-operations as lowercase t and lowercase p, don't be scared, it's easy. I can see some of you already scared. But it will become in the exam tomorrow, so take it easy. So this is not saying anything strange. I'm saying that the latency of each of the subtasks must be better than the latency of the SLA of your service. For example, if we said 100 millisecond P99, each of the sub-services must be completed faster than 100 milliseconds, right? At P99 or better, right? It's obvious, it's stating the obvious. But the question that you need to answer here is that at what percentile you must be faster than 100 milliseconds, right? That's something that usually people miss when they are designing their service, right? Is P99 all right if you are doing 4 operations in your service? And now we're going to answer that. Yeah, it cannot handle that. So the percentile that we need to find, that's the question that we want to answer. What percentile each of those sub-operations must have for your SLA for you to be able to meet your SLA? And the answer to that is basically this. At a percentile that the probability of having all of the sub-operation faster than t is higher than p. This is getting into probability, and I don't want to give you a lesson in probability. But if you convert that sentence into the formula, it's going to be something like this. So the percentile that you are looking for should look like this. Choosing n from n multiplied by the probability of the good thing happening to the power of number of times that good thing you want to happen, which is basically n, multiplied by the possibility of the bad thing happening to the power of times that you want it to happen, which is 0. That's the formula that we need to handle. Choosing n from n is 1. Anything to the power of 0 is 1 as well. So this formula becomes very simple. If you didn't get the previous part, don't worry. The rest of it is going to be very simple. So you want your sub-operation and your SLA have this relationship, which you can simplify to that, and you can simplify to that as well, right? So basically, the percentile that you want to look at for your sub operations must be the nth root of your service SLA, right? That's easy. And if you can make it even more simple. You can put it in a table like this. If the top is the number of the queries, the number of sub operations that you have, and this is the percentile that you are looking at. So if you are looking, for example, at 99 percentile, and the number of operations of 4, you are looking at 0.9975, right? Which if we round it to the closest number of nines, it would be 3 nines. So you have to look at 3 nines. If you look at this, actually, we usually, when we talk about percentiles, when we talk about SLAs, we are talking about 99 percentile. Less than that, usually people don't care much about. If you look at 99 percentile, almost all of them are 3 nines, or 4 nines. None of them are 2 nines. And now when you look at that chart, you understand that why. When you put a fast database and a fast streaming technology next to each other, they usually end up to be very slow. Because if you go to the 99.9 percentile of these technologies, they are actually very slow. In this chart, I'm saying that 99.9 is usually around 100 milliseconds, right? So although the technology, the streaming technology and the database technology on their own are very fast at 99 percentile, when you put them together, the 99 percentile of them is not important. You have to look at 99.9. And then when you do that, you can understand that why it is slow. I'm pretty sure all of you have this experience that you created an application and that application was very fast in dev environment, and you took it to production, and in production everything went wrong and it was very slow, and then you went to the DBAs or DevOps and talked to them and said that what is slow, and they showed you a chart and said that no, it's actually everything is working fine, but the thing that you were getting as the end result was very, very slow. This is the reason for that, because you are not looking at the correct percentile of the performance. So, okay, any questions about this bit? Okay, so now let me give you a little bit of a background about Aerospike. I'm not going to give you too much talk about Aerospike. Aerospike is a NoSQL database like many other databases that you've seen. The main difference that Aerospike has with any other database that you worked with is that it doesn't have a cache in front of the database. Whenever you search anything from Aerospike, we go to the disk and we return the data from the disk to you. All right, so there's only one pathway to get the data to you. We don't have the situation that if the data is in cache, we're gonna give you a good performance. If you go to disk, it's gonna be slow. We always go to disk and we return back the data. But the performance we provide is as if the data was in memory. And we do that with black magic, right? So I don't want to go through that. We sacrifice 3 black goats every night for our Lord and Savior. I'm joking. We just sacrifice 1. But this is the result. When you compare Aerospike with other fast database technologies, we are much faster than them at 99 percentile. You can see that we are around less than 1 millisecond at 99 percentile. But when you go even to 99.9 or 99.99, we are still in a very reasonable latency. And that's why that building a streaming-enabled database with Aerospike actually makes sense. So I have just a quick demo here that I'm not going to walk you through that, but this is showing basically some transactions going through the database. If you look at the Grafana dashboard, this cluster is doing around 200,000 writes per second. The objects are around 1.5 kilobytes. The database is handling 200,000 transactions per second, and this is half an hour, right? I'm not showing you like 5 minutes. It's half an hour. It's doing 200,000 transactions per second. And in that same half an hour, I'm doing 400,000 reads per second, right? And that's not that impressive. A lot of databases can handle that. This is the bit that is impressive. If you look at the latency of reads and writes, 99.9 percentile is 1%. 1 millisecond. And look at that chart. It's just like in that half an hour, doing 400,000 operations per second, right? It's 720 million operations in that half an hour. You see that one dot over there? Only that one dot was 2 milliseconds. Everything else was less than 1 millisecond.
How many nodes?
That's a very good question, because that's the next slide. It's running on 4 nodes of I4I 4x large, which are laptop-sized machines. 16 virtual CPUs, 128 gigabytes of RAM, and less than 4 terabytes of disk. On such an environment, with replication factor of 2, which Aerospike can provide high availability with replication factor of 2, we can store around 3 terabytes of data, and the throughput that the database can handle is around 600,000 operations per second. And the cost on AWS, these are on AWS, is going to be 35K. If you want to run such a workload on AWS Dynamo, it's going to be around $2 million per year. All right, so just to give you an idea about that. And again, I don't want to go through that. The only reason we are here, it's this bit. So the database has some connections. The database basically connects to lots of other technologies. One of those technologies is Kafka. We also connect to Pulsar as well. So we work with lots of different streaming technologies. And the way that it works is that the database can subscribe to a topic, and whenever you write to the topic, the database is going to persist that in the database. And we can also do the other one, which is whenever you write to the database, you can publish it into a topic as well. So the way that the database works is that whenever you write to the database has something called external data center hook that has a basic filter. So the basic filter works like this, that you can say that if the value of the field in that field is true, publish the data. If it is not, don't publish the data. So it's a very basic filter. You can say that if the value does not exist, do this. If the value exists, do that. And then we use that to replicate the data to the other data centers in Aerospike. We can also use that for something called change data capture. That change data capture module that we have is it can handle complex transformations, right? So you can do very, crazy things. You can access to another database and enrich the data and then publish the data. But that thing connects to lots of other technologies, which mainly it's used with Kafka. A lot of our users are using this basically framework to connect our database to other technologies, mainly Kafka. And okay, I don't have the clicker anymore. And we basically end up with something like this. That we said that this is what I call a streaming-enabled database. And as I said, our output connector, the one that can write into the database, is complex, and you can add some filters to that. And we end up with something like that. But as I said, latency is one of the most important parts of this problem. Most people don't use these technologies because the latency is a massive problem. Even the KSQL and Kafka framework, they are using RocksDB in memory because latency is a massive problem. So let's have a look at the latencies that you can get with Aerospike. So we can get 2 milliseconds, from the time that you write into a topic from your client till you can read it from basically an event consumer. It takes around 2 milliseconds at 99 percentile. So assume that we have components. We said that with assuming all of those components at P99 in 2 milliseconds. We said that Aerospike is less than a millisecond latency. So we expect this to be 3 milliseconds, and it is 3 milliseconds. For getting the data out, it takes a little bit longer. It takes 25 milliseconds. And the reason for that is that XDR hook that we have there, it basically publishes data every 20 millisecond out. It basically batches the data, and it doesn't want to just basically constantly send. So it batches things, and it's configurable. It can reduce it to 10 as well, but that's the idea. So okay, that's what we have in our technology and how it integrates with Kafka. So now let's talk about the design patterns. So the first design patterns is very simple. It's asynchronous persistent events. So assume that you have an event producer and an event consumer connecting to each other from using a topic. For some reason, you want to persist these events, so later you can search them. You can, of course, keep them on the topic itself, but imagine that you want to create indices on them and be able to search on them. The common use case for this is that you have an audit use case. So you want to put all of the messages that are going between your microservices, and you want to create some kind of indices on them so the auditor can search them in a later time. And I don't know, this can be a massive database. It can be, I don't know, hundreds of terabytes of data. You can do it, of course, in Kafka, but it's not going to be really that efficient to read the data from, to have a random access to the database. Yeah, that was the example. Next one is a real-time and batch consumer. Right? It's kind of obvious. We discussed that at the beginning of the talk, that you have a real-time user and you have a batch user. You want to use them both. The example of this one is in fraud. So imagine that as the transactions are coming in, you want to check the authenticity of the transaction, but you also want to save that transaction in a lookup table. So in the future calls, you can get into that transaction and solve and basically use that information to figure out if that transaction that is coming in right now is a fraud or not. The next one is persistent event consumer. So again, kinda obvious that what I mean, but the example is going to be more interesting. So imagine you have you build an environment for order fulfillment, and you don't have any system for notifications, right? So you just keep the information, and at some point, you just say that this thing is available. So you can easily add a connector to a topic that's whenever something is changed to fulfilled. You remember I said that the connector that we have as complex events, it can say that whenever that thing happened, or want to produce an event, so you can notify the user, send them a notification, send them an email, an SMS or whatever, to let them know that thing happened. Next one is a selected event consumer. It's not that different. We just added a filter over there. So you are logging a series of events that are happening in your system, and you only want to notify the user if that value is higher than a threshold. If the transaction is higher than £5,000, you want to do some additional checks, so you can send it to an event, so you can check it in a different way. Next one, this is actually very useful. There's a multi-event consumer. So you have several events. Imagine that you go to Amazon and you buy from lots of different vendors. And Amazon want to send you one notification saying that all of the different orders that you made, all of them are fulfilled. All right. So the way that it works is that you write with different writers into the database. Whenever each writer, each provider said that the thing that they want to provide is ready, just write it into the database. But before you publish it, you check the other events, saying that if all the other ones are done as well. If everything else is done, then you can verify the customer. And then finally, the last one is basically you have everything. So you want to handle some real-time events, but at the same time, you want to cache the events for the fast lookups. So you're handling that, but you want to have a fast lookup for the next 30 days. And then also you want to have an event-based system as well that, for example, at the end of each day, you can move everything from the cache into a data lake. So you can have something like this as well. So that was everything. Thank you very much. These are some of the events that we are doing in the next couple of months. I don't know if anybody from Barcelona or anybody from Amsterdam or Berlin is here, but these are some of the events that are happening. We're going to send you some emails with these information as well. So yeah, sign up. We'd like to see you again. Thank you very much.
Thanks, guys. Is there any questions? No questions? I've got some questions.
Go ahead.
What's the best use case you've seen using the technology so far, or innovative use case?
So historically, Aerospike has been really popular in ad tech. So I don't know if you know ad tech, you know, companies that are, whenever you go to a website, they show you a advertisement. Yeah, those guys over there, Virtual Minds, yeah. So they are a customer. Some, basically almost all of the big ad tech companies are Aerospike user because they have very low latency requirements. You know, some people think that oh yeah, my use case is not really that's low latency. It doesn't have low latency requirements. But as you saw, you know, when you look at 99.9, almost everybody has latency problems. So it's usually latency related. Ad tech really understands that. Other industries are coming after that. Now financial services actually quarter by quarter is larger than ad tech now. But the history of the company is mostly in ad tech if you go a few years back.
Any other questions? I've got one more. Might be a bit of a random one. So if someone's trying to break into the streaming industry, what career advice would you give them? So if they're a complete beginner in all of these technologies, like where would you go? What would you learn? What would you do? Yeah. Any advice? It's a minefield these days, but yeah.
Yeah. So I don't know. It's a very difficult thing because, you know, most of my career I've been in the database industry. So before Aerospike, I was in data stacks. Before that, I was a MongoDB developer. Before that, I was a Airspace developer. So I was mostly, you know, database guy. But you know, I remember that. Well, I used Kafka and Pulsar as well. The way that it worked for me was that when it was, believe it or not, it was .NET when .NET introduced Lambda expressions in the language, and .NET 3.3, it was 3, I guess, I can't remember now. When they introduced that, I really liked the idea of just doing everything as streams instead of doing full, and I was just writing the code that nobody else could read. It was just like a bunch of just Lambda functions after each other, and I liked the idea. And then it translated really well to Scala, and then it translated really well to micro batching in Spark, and then it translated really well into Kafka. So, you know, by the time that I got to Kafka, it was like, oh yeah, this is the thing that I've been doing for the past 6-7 years. So it was like that, but I'm ancient, so.
Cool. Thank you very much. Yeah, that's it, guys, for tonight. There's plenty here.
There's a question over there.
Yeah. Sorry.
Data that is stored in Aerospike, in what format, you know, is it? Are there limitations on the number of data formats, you know, supported? And you talk about complex transformations that can be done. Are they constrained by the data format of the data stored?
Yeah. Very good question. So Aerospike is a key value data store, but the value is a nested value, right? So in the value part, you can have a map of a list of a map of a map, right? And then the database understands all of these data structures. So when you are creating an index, you can create an index in the third item of the list that has, I don't know, another list, and I don't know, on the second item of that list. So it is basically like a JSON document. It's literally like that. The language itself is not jQuery, right? But it is very similar to a document store. So the value part is not a dumb value, right? So it can be as complex as your use cases. Nobody want to ask about the color of the goat? No.
I think that's it, guys. So yeah, there's a couple of beers here if you want to grab them freely. It's not going to waste. So yeah, thank you very much, Mike.